Okay, so good morning. I would like first to thank the organizer for giving me the opportunity to present my work. So I'm not an expert in infrared, so I'm very happy to be here and to learn more on infrared. And today I would like to show you how we can use OH lines in the mid-infrared to infer the UV photodissociation rate of water and also the strength of the UV field. So this method can be applied to any molecular environment, but I will mostly focus on disks. So what Colette have already shown you that these beautiful spectra in the mid-infrared, and you can see that the mid-infrared, it's tracing all these warm chemistry, so with HEN, CO2, H2, C2H2, and water. But what you can see here is also this OH line. This seems to be a random line, a tiny line. Actually, it's not a random line because this line is coming from a level that is sitting at 12,000 Kelvin. So no collisions or infrared pumping can excite these lines. Actually, these lines is coming from the photodissociation of water producing OH in rotationally excited states. As proposed by Tape, Carr, and Najita. So in disk, in inner region of disks, all the chemistry is set by by photodissociation. And this is very important because what we want to do in disks is connect this chemistry to the elemental composition in planetary atmosphere. We are only observing HCN, CO2, some specific tracers. So we have to take into account the UV photodissociation of all these molecules. And the big caveat here is that the local UV field is the result of the attenuation of the radiation field, which is very poorly well known. And this is because the attenuation is done by dust. So it depends on dust settling, dust growth, dust composition. The attenuation of the UV field is also very important for the physics of the disk because it controls the coupling between the gas and the magnetic field. So it's important to understand the strength of the UV field for the secular evolution of the disks. So what we propose in this work is to directly measure water photodissociation and the local UV flux from the observation of OH lines in the mid-infrared. So to do so, we used the result from quantum calculation, computing the states of OH following water photodissociation. So these quantum calculations have been done 20 years ago, and the main result is the following. So you can see here a UV spectrum emitting by a typical T-Tauri star. And the result of this quantum calculation is that, well, photodissociation at rather long wavelengths does not produce OH in a rotationally excited state, but at short wavelengths, so short ward of 1040, you see this beautiful distribution. So what I plot here is the probability to form OH in a given rotational state for various vibrational states. So what you can see that we produce mostly OH in a vibrationally ground state, but with very high rotational quantum number, corresponding to energies about 40,000 Kelvin. So very excited. So what we did is to incorporate this quantum data into a molecular excitation code. So we basically compute the excitation level across the full rotational ladder, taking into account the production of OH in high rotational state following water photodissociation, but also taking into account the radiative cascade, collisions, and maybe infrared pumping. And with this model, we can compute the OH line depending on the water photodissociation rate. So here are the results. So without water photodissociation, the OH spectrum is dominated by lines in the mid-infrared regime. So we cannot observe those lines from the ground. It's not very interesting. Those lines are basically excited by collisions or infrared pumping. But when we turn on the water photodissociation, what you can see that all these lines pop up. So it's OH lines. So it's rotational lines coming from levels sitting at a very high energy levels. So those lines are tracing water photodissociation. And what you basically see in those lines is the radiative cascade of OH following its production in high rotational quantum number. So you can see that we can observe these lines in the Q and N band. What can we measure from these lines? So somehow you can feel that the line intensity depends on the strength of the UV photodissociation. Well, what I'm showing here is the line intensity as a function of the column density of water photodissociated per unit time. And what you can see that this line intensity in the mid-infrared is perfectly proportional to the column density of water photodissociated per second. So this is really what you can measure with these lines. So it's very simple, and you can apply this to protoplanetary disks. So you can see here line flux for a large sample of protoplanetary disks, so ordered as a function of this accretion luminosity. So you can directly convert this line flux into an amount of water photodissociated per unit time. So this is what I did here. So expressed in Earth ocean per day. And what you can see is that basically in theta ray disks, about 1 Earth ocean is photodissociated per day, which is a huge quantity. And it's a very direct measurement. Well, disks are a very complex structure. So in the paper, we rather apply this model to what we think is a simpler situation. This is a bow shock. This is the apex of the bow shock created by a protostellar jet impacting the surrounding medium. And at the apex of the bow shock, you have a very strong shock producing UV. So it's a very good proxy for a protoplanetary disk. You have a very rich chemistry with a lot of molecular tracers and a source of UV. And what Tape have observed with Spitzer is this beautiful sequence of rotationally excited OH lines. And so with these lines, we can, well, fit these lines with our model and deduce an amount of water photodissociated per time. And in that object, we derive about 1 Northy every 2 minutes. So it's a softer photodissociation rate, amount of water photodissociated per second. Well, this amount of water photodissociated per second is an interesting quantity, but what we want to measure is the UV field. And this is not what we measure when we measure line intensities. Well, actually, if you are able to measure the column density of water, then you can compute the ratio between the column density of water photodissociated per unit time divided by the column density of water. And this quantity is the photodissociation rate of water that is directly proportional to the UV flux. So if you have a column density of water, you can measure the UV flux. So we did this job in HH211, sorry, with the Spitzer lines, and we derived a UV flux that is 5,000 times larger than the interstellar UV flux. So quite strong UV flux. Well, as a conclusion, so OH line in the mid-infrared are very good way to derive the column density of water photodissociated per second. It's really model independent. It doesn't depend on the temperature of the gas, of the density of the gas. If you have a column density of water, then you can derive the local UV field. And this is with ELT-METIS, it's very promising because with ELT-METIS, we'll have access to the spatial distribution of the OH emission. So we will be able to measure the intensity of the mid-infrared lines at the function of the distance, and maybe the water line at the function of the distance, either near or mid-infrared lines. And with these data, we will be able to map the local UV field in the molecular layer as a function of the distance. With this quantity, we will be able to assess the role of photodissociation onto the molecular abundances that we derive. We'll be able to constrain the dust properties because we will have access to the attenuation of the radiation field, and also understand the coupling between the gas and the magnetic field. Thank you very much for your attention. Sorry.
Okay, thank you, Benoît. There's a question from Uli. Benoît, can you comment whether you would also see OH lines in the near IR, like the ones we get from Earth's atmosphere?
So yeah, it's a good question. So I'm not an expert on infrared. So yeah, we will be contaminated also by air glows. So you really have to play with the Doppler shifts in your observation. So yeah, it might be quite tricky.